What if the darkest objects in the universe began as an idea centuries before anyone believed they were real? Welcome to Sleepy Cosmic Lore. Tonight, we'll follow the history of black holes, from the first dark stars imagined before Einstein, through collapsing giants and hidden galactic monsters, to gravitational waves and the first image of a black hole's shadow. Settle in, let your mind drift through the darkness, and subscribe for more calm journeys into the mysteries of space. Long before anyone spoke of curved spacetime, event horizons, or singularities, the first shadow of a black hole appeared in the mind of a quiet English clergyman who had never seen anything beyond the solar system with more than a modest telescope. It was the late 18th century, an age of candlelit studies, brass instruments, handwritten calculations, and night skies still untouched by electric light. Astronomers knew that stars were distant suns, but they had little idea what powered them, how long they lived, or what happened when they died. No one knew that the Milky Way was only one galaxy among an almost unimaginable number of others. There were no photographs of nebulae, no radio telescopes, no spacecraft, and no theory explaining how gravity could reshape space and time. Yet hidden inside the familiar laws of Isaac Newton was a question that would eventually lead toward one of the strangest objects in the universe. How powerful could gravity become before light itself was unable to escape? The man who asked that question was John Michell, born in England in 1724. Michell was a clergyman, but in the intellectual world of his time, that did not prevent him from becoming a serious investigator of nature. He studied magnetism, geology, earthquakes, gravity, and the arrangement of stars. He was not a public scientific celebrity, and much of his life passed far from the grand institutions usually associated with major discoveries. What made him exceptional was the way he looked for invisible causes behind visible effects. When the ground shook, he imagined waves traveling beneath the surface. When two stars appeared close together, he considered whether gravity might bind them rather than assuming their alignment was accidental. And when he thought about light leaving a star, he asked whether the star's own gravity might change what an observer far away would see. To follow Michell's reasoning, we have to enter a version of the universe that was logical in the 18th century, but very different from the one described by modern physics. Newton's theory of gravity had transformed science. It explained falling objects, the orbits of planets, the paths of comets, and the motion of the moon through one universal principle. Every mass attracted every other mass, and that attraction weakened with distance. Light, meanwhile, was often imagined as a stream of extremely small particles moving at tremendous speed. This particle picture was not complete, but it gave Michell a path toward a disturbing possibility. If light consisted of particles, and if those particles moved through the gravitational field of a star, perhaps gravity could slow them, just as Earth's gravity slows a stone thrown upward. The logic began with escape velocity. Throw a stone gently into the air, and it rises briefly before falling back. Launch it faster, and it climbs higher. Increase its speed enough, and it can escape Earth entirely, not because gravity disappears, but because the object keeps moving outward while gravity weakens with distance. Every world has an escape velocity determined by its mass and size. The Moon's is lower than Earth's. The Sun's is much greater. A body that packed enormous mass into a sufficiently small region would demand an even higher speed from anything trying to leave its surface. By Michel's time, astronomers also knew that light did not travel instantaneously. Observations of the moons of Jupiter had revealed that light moved at a finite, measurable speed. Once Michel combined this fact with Newtonian gravity, the question became unavoidable. Could a star be so massive that its escape velocity equaled the speed of light? And if it became even more massive, what would happen to the light leaving its surface? In Michel's model, light particles would rise away from the star, lose speed under the pull of gravity, come to a halt, and fall back. The star could remain enormous, hot, and physically present, yet no light from it would ever reach a distant observer. The night sky might therefore contain gigantic bodies, hidden not by distance or dust, but by their own gravitational power. In 1783, Michel presented this idea in a paper sent through the scientist Henry Cavendish and later published by the Royal Society. His calculations suggested that a star with roughly the same average density as the Sun, but a diameter about 500 times larger, would have an escape velocity comparable to the speed of light. The result was based on Newtonian physics, and the imagined object was very different from a modern black hole. Michel's dark star still possessed a material surface. Space remained a fixed stage around it. Time flowed normally everywhere. Gravity acted as a force pulling light particles backward. There was no event horizon, no curved spacetime, and no region where every possible path into the future pointed inward. Light failed to escape because it was treated like a projectile that had not been launched fast enough. In a true black hole described by general relativity, light always moves locally at the same speed. It is the geometry of spacetime that prevents its outward journey from leading anywhere beyond the horizon. Michel had not predicted that deeper structure, and it would be misleading to claim that he had somehow discovered modern black holes more than a century before Einstein. What he had done was different, but still remarkable. He had pushed the accepted physics of his age to an extreme and uncovered the outline of an invisible gravitational object. Even more impressively, he understood that invisibility did not make such an object impossible to detect. Michel considered a dark star that belonged to a binary system, orbiting together with a normal, luminous star. The dark object itself could not be seen, but the visible companion would move under its gravitational influence. By tracking that movement, an astronomer might infer the existence and mass of the unseen body. This idea was far ahead of the instruments available to Michel, yet the method would later become one of the main ways astronomers identified black hole candidates. A visible star could appear to orbit empty space. Its speed and path could reveal the mass of whatever remained hidden. If the unseen companion was too massive and compact to be an ordinary star, a white dwarf, or a neutron star, a black hole would become the strongest explanation. Michel had grasped a principle that remains central to astronomy. Darkness can be measured by what it makes other things do. A similar possibility appeared in France a few years later through the work of Pierre-Simon Laplace. one of Europe's most powerful mathematical thinkers. In an early edition of his book on the system of the world, Laplace suggested that there might be luminous bodies so massive that their light could never reach us. Whether he developed the idea entirely independently or encountered some form of Michel's reasoning is difficult to determine with certainty. But the important point is that the concept was not merely a strange private fantasy. It emerged naturally from the physics of the period. If gravity acted on light particles, and if the speed of light was finite, then an object massive enough to imprison its own light seemed mathematically possible. For a brief moment, the universe appeared capable of hiding some of its largest stars in plain sight. Yet the idea did not grow into a major field of research. Instead, it gradually disappeared. The reason was not that astronomers discovered evidence proving dark stars could not exist. The deeper problem was that the theory of light supporting the argument began to lose ground. During the early 19th century, experiments involving interference and diffraction showed that light behaved in ways strongly associated with waves. When light passed through narrow openings or overlapped with itself, it produced patterns of brightness and darkness that the simplest particle theories struggled to explain. The wave theory became increasingly successful, and Michel's original picture became harder to defend. If light was a wave rather than a stream of ordinary particles, what exactly would it mean for gravity to slow it below its escape velocity? Would a wave respond to gravity in the same way as a thrown stone? What medium carried that wave? And how would the medium behave near an enormously massive star? 19th century physics had no complete answers. There was no accepted theory connecting gravity to the propagation of light, so the dark star lost the intellectual foundation that had made it appear plausible. Laplace removed the discussion from later editions of his work. The concept was not destroyed in a dramatic debate. It simply faded as scientists turned toward theories that seemed more productive and easier to test. The instruments of the age offered little reason to keep pursuing it. Telescopes could not reliably detect the subtle orbital effects of distant, invisible objects, and astronomers did not yet understand the internal lives of stars. They knew almost nothing about nuclear energy, stellar fusion, electron pressure, neutron matter, or gravitational collapse. Michel could calculate the properties of a dark star, but no one could explain how nature might actually build one. His imagined object was a star of roughly solar density expanded to an almost absurd size, not the compressed remnant of a dying massive star. Without a mechanism of formation and without observational evidence, the dark star became a mathematical curiosity rather than an expected part of the cosmos. This is where the history becomes more revealing than a simple tale of a forgotten genius. Michel's reasoning was not entirely correct, yet it pointed towards something real. The scientific framework around it was not strong enough to carry the idea forward. A discovery can appear before its time not because people are unwilling to understand it, but because the necessary network of theories, instruments, and observations does not yet exist. Through the 19th century, researchers learned to analyze starlight, identify chemical elements in distant suns, measure stellar motion, and unite electricity with magnetism. Physics advanced enormously, but the possibility of a body from which light could not escape remained mostly abandoned. The irony is that the wave theory that helped bury Michel's dark stars did not make gravity irrelevant to light. It only revealed that the old explanation was too simple. Light would eventually prove capable of behaving like both waves and particles, while gravity would turn out not to be a conventional force acting across an unchanging emptiness. The true breakthrough would require scientists to stop asking whether gravity could slow a particle of light and begin asking whether gravity could change the structure of the path itself. A black hole would not be understood as a giant star pulling rays backward from its surface, but as a region where space-time had been shaped so completely that outward escape was no longer part of any possible future. Michel and Laplace had reached the edge of that idea without possessing the language needed to cross it. Their dark stars vanished from scientific attention, leaving behind a question that would wait for more than a century. Then, a new theory of gravity would appear, and the abandoned darkness of the 18th century would return, not as an oversized hidden star, but as a doorway in space-time from which nothing could come back. By the opening years of the 20th century, gravity had become the most successful theory in science and one of its deepest problems. Newton's equations could predict the paths of planets with astonishing precision, yet they carried an unsettling implication. Gravity seemed to act across empty space instantly. Move the sun, and in Newton's picture, Earth would somehow respond at once, no matter how great the distance. That did not fit the new world Albert Einstein had revealed in 1905, where no signal, influence, or piece of information could travel faster than light. The conflict was not a small technical flaw. It suggested that either Newton's gravity or Einstein's new understanding of space and time had to change. Einstein spent the next decade searching for a theory that could preserve both the power of gravity and the speed limit imposed by light, and the path was anything but direct. He began with a thought that seemed almost too simple to transform physics. Imagine a person sealed inside an elevator with no windows. If the elevator were standing on Earth, the person would feel weight pulling them toward the floor. But if the same elevator were far from every planet and accelerating upward through empty space, the person would also be pressed against the floor. From inside, the two experiences could be indistinguishable. Gravity and acceleration, Einstein realized, were not merely similar. Locally, they might be two descriptions of the same physical situation. This became the equivalence principle, the first clue that gravity was not an ordinary force reaching through space. If acceleration could imitate gravity, then light itself should appear to bend inside an accelerating room. A beam crossing the elevator would travel in a straight line, but while it moved, the floor would rise, making the beam seem to curve downward. If gravity and acceleration were equivalent, light passing near a massive object should also follow a curved path. Yet light could not simply be treated as a slow projectile being dragged sideways. In Einstein's developing picture, the geometry through which the light moved had to be changing. Space was no longer an invisible stage on which matter performed. Time was no longer a universal clock ticking identically everywhere. Together, space and time formed a flexible structure that could be distorted by mass and energy. A planet orbiting the Sun was not being pulled across a rigid emptiness in quite the old sense. It was following the straightest path available through curved space-time, much as an airplane can follow what appears to be a curved route on a flat map, while actually tracing a natural path across the round surface of Earth. The analogy was imperfect, but it captured the revolution. Gravity might be geometry. Einstein struggled for years to turn that intuition into a working set of equations. He had to learn unfamiliar mathematics, correct false starts, and compete with others racing toward similar ideas. By November 1915, after weeks of intense work, he presented the final form of the field equations of general relativity. On one side stood the distribution of matter and energy. On the other stood the curvature of spacetime. The equations did not merely say that matter attracted matter. They described a universe in which matter told spacetime how to curve, while curved spacetime guided matter and light. Almost immediately, the new theory explained a small but persistent irregularity in the orbit of Mercury that Newtonian gravity had not fully accounted for. It also predicted that light passing near the Sun would be deflected by an amount larger than earlier Newtonian estimates. These successes made general relativity more than an elegant speculation. But the equations were so difficult that even Einstein could solve them exactly only in limited cases. Then, from the middle of a war, came a solution he had not expected. Karl Schwarzschild was a German physicist, astronomer, and gifted mathematician serving on the Eastern Front during World War I. Despite illness, military duties, and the conditions surrounding him, he studied Einstein's newly published theory and found an exact solution within weeks. Schwarzschild considered an idealized situation: a perfectly spherical, non-rotating mass with no electric charge, surrounded by empty space. The model was simple compared with a real star, yet what emerged from it was not simple at all. His solution described how clocks, distances, and paths of light behaved outside a spherical body. Far away, spacetime looked nearly flat and familiar. Closer to the mass, the distortion grew stronger. Time passed differently relative to distant observers. Light was bent. The geometry tightened around the object, and inside the mathematics appeared a particular radius where the equations seemed to break. Today, that distance is called the Schwarzschild radius. Its size depends only on the mass of the object. The more mass, the larger the radius. For the Sun, it would be only about 3 kilometers. For Earth, less than a centimeter. This did not mean the Sun or Earth were black holes. Their matter lies far outside those limits. But the equation raised a chilling possibility. If any mass could somehow be compressed within its Schwarzschild radius, the surrounding geometry would become so extreme that the boundary at that radius would behave unlike any ordinary surface. Early interpretations were confused because the original mathematical coordinates made certain quantities appear infinite there. It looked as though time froze, space stretched without limit, and the theory collapsed at the boundary. Some physicists suspected that the strange radius marked a genuine physical disaster. Others believed it was merely an artifact of the way the coordinates had been chosen, like the apparent breakdown of longitude at Earth's poles. Every line of longitude meets at the pole, but the planet itself does not tear apart there. The map fails, not the landscape. The same distinction would become crucial in understanding Schwarzschild's solution. The radius was not necessarily a place where local physics became infinite. A falling observer could cross it without encountering a solid wall or a sudden rupture, especially if the black hole were large enough that tidal forces there were mild. What changed was the relationship between the region inside and the universe outside. Once the boundary was crossed, every future directed path led farther inward. Escaping was not forbidden because a traveler lacked a powerful enough engine. It was forbidden because no outward route remained in the structure of space-time. Even light, always moving locally at light speed, could not find a path leading back out. The boundary would later be called the event horizon, a name that captured its true meaning. It was not the place where matter necessarily ended, but the edge beyond which events could no longer influence distant observers. From outside, signals emitted by an object falling toward the horizon would arrive increasingly delayed and redshifted, fading as their wavelength stretched. The object would appear to slow and dim near the boundary. Yet from the perspective of the falling object, the crossing could occur after a finite amount of personal time. These two descriptions were not contradictory. They arose from different ways of slicing space-time into space and time, a reminder that general relativity had made the observer's position part of the story. But the solution contained another, darker feature. At the center, the mathematics indicated a true singularity, a region where curvature grew without bound in the classical theory. Unlike the apparent problem at the horizon, this could not be removed merely by changing coordinates. Whether such a singularity represents a literal, physical point of infinite density, or instead signals the failure of general relativity, remains an open question. Most physicists expect that a complete theory of quantum gravity would alter the description at extremely small scales, but no experimentally confirmed theory yet tells us exactly what replaces the singularity. In 1916, however, the distinction between horizon and central singularity was far from clear. Schwarzschild himself died only months after publishing his solution, leaving others to argue over what it meant. Many scientists doubted that nature could ever create an object compact enough to expose the strange region in the equations. Real stars were not perfect spheres frozen in empty space. They rotated, emitted radiation, contained pressure, and were made of matter that might resist compression. Perhaps the critical radius was a mathematical curiosity, never reachable by any physical process. Even Einstein remained skeptical that such complete collapse could occur in reality. His theory allowed the possibility, but he did not immediately accept that the universe would make use of it. That hesitation was understandable. General relativity had revealed a door in the mathematics, but no one yet knew whether any star could be forced through it. The Schwarzschild solution described the space-time outside a compact mass. It did not explain how an ordinary star could lose its support, shrink past the critical radius, and form an event horizon. That required a theory of stellar interiors and a better understanding of what held stars up against gravity. At the time, even the source of starlight was not fully understood. Nuclear fusion had not yet been established. Quantum mechanics was only beginning to emerge. The extreme states of matter that might appear inside dying stars remained unknown. So the most disturbing implication of Einstein's theory waited in a strange scientific limbo. The equations seemed to permit a region from which no message could return, yet the physical path to such a region was missing. For years, the boundary was discussed under awkward names such as the Schwarzschild singularity or the gravitationally completely collapsed object. The modern language of black holes, horizons, and trapped surfaces had not yet been developed. Still, something irreversible had happened. Gravity was no longer simply a force that could become stronger and stronger. It had become capable at least in theory, of reshaping causality itself. Schwarzschild had taken Einstein's equations and discovered that they contained a one-way threshold, a place where the future tilted inward and escape stopped being a meaningful option. The universe had acquired a hidden architecture no one had anticipated. The next question was no longer whether the equations allowed such a doorway, but whether a real star, after exhausting the forces that supported it, could be driven all the way through. The missing piece was matter. Einstein's equations had shown what spacetime could become around a sufficiently compact mass, but they did not explain whether a real star could ever be forced into that condition. Stars were not silent mathematical spheres. They burned, rotated, pushed outward, shed material, and held themselves up through layers of pressure that no one yet fully understood. To decide whether one could truly collapse beyond recovery, physicists first had to answer a more basic question. What stops a dead star from falling forever? In 1930, a 19-year-old Indian physicist named Subrahmanyan Chandrasekhar boarded a ship bound for England and spent part of the voyage thinking about white dwarfs, the dim, compact remains of stars like the Sun. A white dwarf contains roughly a star's mass squeezed into a body about the size of Earth. Gravity there is fierce, yet the object does not continue shrinking. Its support comes from quantum mechanics, specifically from the refusal of electrons to occupy identical states. Even after ordinary heat has faded, compressing the electrons into a smaller volume forces them into increasingly energetic motions, creating what physicists call degeneracy pressure. It is not pressure in the familiar sense of hot gas pushing against a container. It is built into the quantum rules governing matter. A cold white dwarf can therefore remain stable for an immense span of time, balanced between gravity pulling inward and electron degeneracy pushing back. But Chandrasekhar noticed that this balance contained a hidden weakness. As a white dwarf became more massive, its electrons had to move faster to resist the increasing weight. Eventually, their speeds approached the speed of light, and relativity changed the way their energy and pressure increased. Gravity kept growing stronger with added mass, but the quantum support could no longer strengthen quickly enough to match it. The calculation led to a critical boundary, now known as the Chandrasekhar limit, near 1.4 times the mass of the Sun, though the precise value depends somewhat on composition and other physical details. Above that limit, a stable white dwarf could not exist. This was not yet a prediction of a black hole. Chandrasekhar's work did not tell nature exactly what came next. It revealed something almost more unsettling. One of the known ways a dead star could resist gravity simply stopped working beyond a certain mass. The equations had removed a flaw, leaving the star with nowhere obvious to stand. When Chandrasekhar arrived in Cambridge, he entered a scientific world dominated by Arthur Eddington, the astronomer who had helped bring Einstein's theory to international attention and developed an influential picture of stellar balance. Eddington understood how delicate a star's equilibrium could be, but he found Chandrasekhar's conclusion physically intolerable. If electron pressure failed, what prevented a massive stellar core from collapsing toward an absurdly dense state? Eddington suspected that some unknown law of nature must intervene before matter reached such an extreme. In 1935, at a meeting of the Royal Astronomical Society, the disagreement became public. Chandrasekhar presented his analysis. Eddington challenged the conclusion before the audience, arguing that nature should not be driven into what he regarded as a pathological result. The encounter was painful for the younger scientist and helped delay broad acceptance of the limit, although other physicists gradually recognized the strength of the mathematics. It is tempting to turn the episode into a simple drama in which a courageous young genius defeats a stubborn authority. But that version hides the uncertainty of the time. The interior of a star was still a frontier. Nuclear fusion was only beginning to be understood. The neutron had been discovered by James Chadwick in 1932. No one possessed a reliable description of matter compressed far beyond white dwarf density. Eddington was wrong to dismiss the result, but his instinct that unknown physics might appear at higher densities was not unreasonable. The real question was whether that new physics would halt collapse or merely postpone it. The neutron offered the first possible answer. Because neutrons carry no electric charge, matter made largely from them could be packed far more tightly than ordinary atoms. In 1934, Walter Baade and Fritz Zwicky proposed that supernova explosions might mark the transformation of ordinary stars into neutron stars, compact remnants in which matter had been crushed to nuclear density. A neutron star could place more than the Sun's mass inside a sphere only tens of kilometers across. Its surface gravity would be enormous. Yet even this extraordinary object was not infinitely compressible. Neutrons are quantum particles, and their degeneracy pressure can resist gravity much as electron degeneracy supports a white dwarf. Nuclear interactions between particles also matter, but once again, the balance has limits. In 1939, Robert Oppenheimer and George Volkoff examined neutron cores using general relativity and found that sufficiently massive ones could not remain in stable equilibrium under the assumptions available to them. Modern estimates of the maximum neutron star mass are more refined and depend on the still uncertain behavior of matter at extreme density. But the principle survives. Beyond some threshold, even neutron pressure cannot guarantee support. The ladder of stellar survival was running out of rungs. Ordinary gas pressure could support a shining star while nuclear reactions continued. Electron degeneracy could support a white dwarf after the fuel was gone. Neutron pressure could support an even denser remnant. But for a core carrying too much mass, every known defense appeared capable of failing. The possibility that had once seemed like a strange feature of a spherical solution was becoming the possible endpoint of stellar evolution. Oppenheimer then turned to the next stage with his student Hartland Snyder. Their 1939 paper on continued gravitational contraction considered an idealized star made of pressureless matter collapsing under its own gravity. The model was deliberately simple, perfectly spherical, non-rotating, and free of the complicated pressure, magnetic fields, turbulence, and radiation found in real stars. That simplicity allowed them to follow the collapse with general relativity and see something no earlier stellar model had shown so clearly. For an observer remaining far away, the surface of the collapsing star appeared to move ever more slowly as it approached the critical boundary. Its light became increasingly redshifted, weakened, and delayed. The star seemed to freeze and fade, leaving behind a dark gravitational field. But for matter falling with the star, the story was different. The surface crossed the critical radius in a finite amount of its own time and continued inward. The boundary was not a material shell stopping the collapse. It was the point beyond which the future of the falling matter could no longer reconnect with the outside universe. Oppenheimer and Snyder had produced the first detailed model showing how gravitational collapse could create the object later called a black hole. Their calculation also exposed a strange split in perspective that would haunt black hole physics for decades. To distant eyes, collapse seemed never quite to finish. To the collapsing matter, it did. Neither viewpoint was simply an illusion. Each followed from how time is measured in curved spacetime. The star did not vanish in a sudden flash behind a visible wall. Instead, its final signals stretched, reddened, and slipped toward silence. The universe outside retained the star's gravitational influence, but lost access to the events unfolding deeper within. In modern language, an event horizon formed. The phrase did not yet belong to the standard vocabulary, and Oppenheimer himself did not fully pursue the subject after this work. Within months, Europe was at war. Physics shifted toward nuclear fission, radar, and weapons research. Oppenheimer's name would soon become inseparable from the atomic bomb, rather than collapsing stars. The 1939 paper remained known to specialists, but did not ignite an immediate revolution. There were also legitimate reasons for caution. A real dying star is not a perfectly smooth ball of pressureless matter. It may rotate rapidly, explode asymmetrically, throw off much of its outer mass, or contain magnetic fields strong enough to reshape its surroundings. Perhaps these complications would always prevent complete collapse. Perhaps a star would fragment, bounce, or settle into an unknown state before a horizon formed. The model demonstrated that collapse was possible under specific assumptions. It did not yet prove that nature would produce black holes robustly in the messy universe. Still, the direction of the evidence had changed. The problem was no longer a mysterious radius waiting inside an abstract equation. Stellar physics had begun to reveal a sequence of failures, each occurring when gravity overwhelmed another form of support. Chandrasekhar showed that white dwarfs had a maximum mass. The discovery of neutron matter offered a denser refuge, but Oppenheimer and Volkoff found that refuge could also end. Oppenheimer and Snyder then followed matter beyond the final balance and watched space-time close around it. The most disturbing part was not that gravity destroyed the star. Stars explode and shed their layers all the time. It was that after enough mass crossed the threshold, no pressure acting later from within could send news of recovery to the outside. Collapse became more than compression. It became a change in what events were allowed to influence one another. Yet the scientific community was not ready to accept that this austere model described real objects scattered across the sky. The mathematics had reached the edge, but observation had not followed. The next generation would have to decide whether horizons survived rotation, irregularity, and imperfect collapse, and whether the universe truly contained these one-way regions, or whether some overlooked law of nature always intervened before the door could close. For nearly 2 decades, the collapsed stars described in the late 1930s remained buried beneath other priorities: war, had redirected the most brilliant physicists toward radar, nuclear weapons, and particle research, while general relativity came to seem like an elegant but isolated theory, admired for its beauty and avoided for its difficulty. The equations still contained regions where gravity could seal off the future. Yet few researchers treated those regions as objects likely to exist in the sky. They were discussed as frozen stars, collapsed configurations, or peculiar singular solutions, phrases that sounded more like warnings inside mathematics than names for real things. Then, during the 1950s and 1960s, several developments converged and forced the old problem back into view. Better mathematical tools revealed that the apparent breakdown at the critical boundary was not a physical catastrophe. New astronomical discoveries showed that the universe contained far more violent sources of energy than anyone had expected. And a younger generation of physicists began to treat Einstein's theory not as a completed monument, but as unexplored territory. One of the first obstacles was the misleading way the original equations described the horizon. In the usual coordinates, a falling object appeared to slow forever as it approached the critical radius, while certain mathematical quantities seemed to become infinite there. This made the boundary look like a frozen surface where the theory stopped making sense. But a coordinate system is only a way of labeling events, and the wrong labels can create false disasters. The surface of Earth offers a simple example. Longitude becomes undefined at the poles, yet nothing unusual happens to a traveler standing there. The map fails, not the landscape. In the same way, physicists including David Finkelstein, Martin Kruskal, and George Sekaresh developed descriptions that passed smoothly across the supposed barrier. Their work showed that the critical surface was not a place where space-time tore apart. It was a one-way boundary. Matter could cross inward, but after crossing, no future path led back to the exterior. Finkelstein's 1958 interpretation was especially important because it made the physical meaning difficult to ignore. He described the surface as a membrane moving only one way through causality, not a material shell, but a division between events that could still communicate with the distant universe and events that could not. The frozen star was not frozen from its own point of view. The freezing occurred only in the increasingly delayed and weakened signals received far away. Once the misleading coordinates were removed, the horizon stopped looking like an error and began to look like a real feature of spacetime. This shift changed the central question. Researchers no longer had to ask whether the mathematics behaved strangely at the boundary. They had to ask whether the boundary would survive in realistic collapse. Perfectly spherical stars were convenient, but real stars spin, pulse, carry magnetic fields, and collapse unevenly. If a horizon required flawless symmetry, nature might never produce one. The breakthrough came from studying gravity in a more global way, without relying on a special coordinate system or an idealized shape. Roger Penrose approached the problem by asking how light itself behaves when gravity becomes strong enough to trap it. Imagine a sphere surrounding a normal star. Some beams of light move outward, increasing the size of the sphere they occupy, while others move inward. But in a sufficiently collapsed region, gravity can become so severe that even the outward-directed light rays begin converging. Penrose called such a configuration a trapped surface. Once it formed under physically reasonable conditions, The future development of spacetime could not remain complete and regular according to classical general relativity. His 1965 singularity theorem showed that gravitational collapse did not need to be perfectly spherical to drive spacetime toward a singular outcome. Irregularities, distortions, and realistic departures from symmetry did not automatically rescue the star. The theorem did not describe what the singularity physically was, nor did it prove that classical infinities must survive in a future quantum theory. What it established was more immediate. The catastrophic conclusion was built deeply into general relativity, not inserted by an unrealistic model. This was one of the moments when collapsed objects stopped being mathematical curiosities and became unavoidable consequences of the theory under certain conditions. At almost the same time, another discovery widened the range of possible objects. In 1963, New Zealand mathematician Roy Kerr found an exact solution describing the spacetime around a rotating mass. This mattered because nearly everything in the universe rotates. Stars spin, galaxies turn, and collapsing matter carries angular momentum that cannot simply disappear. The Kerr solution revealed an object more complex than the non-rotating case. Outside its horizon lay an ergosphere, a region where space-time itself was dragged around so strongly that nothing could remain stationary relative to distant space. A traveler there might still escape, but could not resist being carried in the direction of the rotation. In principle, energy could even be extracted from this spinning geometry, a possibility later explored through processes involving particles and magnetic fields. Yet the rotating solution also introduced deeper structures inside the horizon, including an inner horizon and a ring-shaped singularity in the idealized classical description. Whether all of those internal features survive disturbances in realistic black holes remains a difficult question. Small perturbations may radically change the interior, and modern research continues to examine how stable those regions truly are. From the outside, however, Kerr's result gave physicists something powerful, a realistic candidate for the final state of rotating gravitational collapse. As the theory matured, researchers discovered an unexpected simplicity. A star can begin with complicated layers, turbulence, magnetic fields, chemical differences, and surface features. But after collapse and the emission of gravitational radiation, the settled object appears to lose almost all visible memory of that complexity. In classical general relativity, an isolated black hole can be described externally by only a few properties: mass, angular momentum, and electric charge. Astrophysical black holes are expected to carry little lasting net charge because surrounding plasma would quickly neutralize them, leaving mass and spin as the main quantities. This emerging principle became known informally as the no-hair idea, suggesting that black holes have no detailed external features revealing what formed them. The phrase was memorable, but the underlying results came from years of mathematical work by several physicists, including Werner Israel, Brandon Carter, and David Robinson, under specific assumptions about stability and isolation. The conclusion was not that every possible object in every alternative theory must be identical, but that the black holes predicted by ordinary four-dimensional general relativity were astonishingly limited in how much information they displayed from the outside. A collapsed star could begin as a chaotic furnace and end as an almost pure gravitational object. This was both elegant and disturbing. If the details of the original matter disappeared from external view, where did that information go? At the time, the question had not yet become the full quantum crisis it would later become, but the tension was already present. The subject also needed a name. Technical phrases such as gravitationally completely collapsed object were accurate enough to discourage almost anyone from saying them twice. The expression black hole had appeared in scattered contexts before it became standard, and its exact first use in the modern scientific sense is not completely straightforward to trace. What is clear is that John Archibald Wheeler played the decisive role in popularizing it during the late 1960s. Wheeler was a gifted physicist and an unusually vivid communicator who believed that powerful ideas needed language sharp enough to make them visible. During a lecture in 1967, after repeated descriptions of total gravitational collapse, the shorter phrase was suggested or adopted: black hole. It captured the essential image immediately. The object was black because light could not escape from inside its horizon, and it resembled a hole because anything crossing the boundary disappeared from the accessible universe. Yet the name was also misleading in useful ways. A black hole is not an empty cavity punched through space. It may contain the mass of many suns. It does not behave like a cosmic vacuum cleaner, pulling in everything around it. Far from the horizon, its gravity is no stronger than that of any other object with the same mass. If the sun could somehow be replaced by a black hole of equal mass, Earth would continue along nearly the same orbit, although the loss of sunlight would quickly destroy the conditions that support life. The danger comes not from a mysterious extra attraction, but from concentrating mass so tightly that extreme space-time curvature becomes accessible. Wheeler's phrase gave the idea cultural force at the exact moment the physics was becoming credible. A concept that had once been hidden behind equations could now be spoken in two ordinary words. Researchers could ask how black holes formed, whether they were stable, how they interacted, and what observations might reveal them. The name did not solve the scientific problems, but it changed the way the problems could be imagined. By the end of the 1960s, the theoretical case had become far stronger than it had been a generation earlier. Horizons were no longer dismissed as coordinate mistakes. Collapse no longer depended on perfect symmetry. Rotating solutions existed. Mathematical theorems showed that singular behavior followed under broad conditions. The objects had acquired a simple external description and, finally, a name that would not be forgotten. Yet the most important evidence was still missing. Every advance so far had come from equations. The universe had not placed a black hole inside a laboratory or shown one directly through a telescope. To move from possibility to discovery, astronomers would need to detect an object defined by the absence of escaping light. The solution would come from an unexpected direction, not by searching for darkness itself, but by finding some of the brightest and most violent radiation ever observed. The first convincing signs did not come from darkness at all. They arrived as bursts of energy so violent that astronomers had to invent new ways of seeing the sky. By the early 1960s, radio telescopes were revealing compact sources that looked almost like stars in ordinary photographs, but poured out enormous amounts of radio energy. One of them, 3C273, became the turning point. In 1963, Martin Schmidt recognized that its strange spectral lines were not unfamiliar elements, but familiar hydrogen lines shifted far toward the red, meaning the object was receding at tremendous speed and therefore lay at a vast cosmological distance. If something so far away could still appear so bright, it had to be producing more energy than an ordinary galaxy, while shining from a region that seemed astonishingly small. These objects became known as quasars, short for quasi-stellar radio sources, though not every quasar is especially strong in radio waves. Their existence created an immediate crisis of scale. A normal star could not power them. A whole galaxy of stars could not easily explain how quickly their brightness changed. Some quasars varied over months, weeks, or even shorter intervals, implying that much of their light came from a region no larger than the distance light could cross during that time. The source was not only brilliant, it was compact. Something near the center of a distant galaxy was converting mass into radiation with an efficiency far beyond ordinary nuclear burning. The emerging answer was almost perverse. The brightest persistent objects in the universe might be powered by things that were themselves completely dark. Matter approaching a black hole does not simply fall straight through the horizon like water down an open drain. Gas usually carries angular momentum. Instead of plunging directly inward, it circles, collides, and spreads into a rotating accretion disk. Magnetic turbulence and related processes transfer angular momentum outward, allowing some material to spiral inward. As the gas descends deeper into the gravitational field, part of its potential energy becomes heat and radiation. Near a compact object, that energy release can be extraordinary. A feeding black hole may therefore be surrounded by a region brighter than billions of stars, even though the black hole itself contributes no light from inside the horizon. Astronomers would not identify black holes by photographing their surfaces. They would look for the final blaze of matter before it disappeared. Quasars suggested that supermassive black holes might exist in distant galactic centers, but the interpretation was not immediately settled. Alternative ideas were considered, including chains of supernovae, unusual stellar systems, and other exotic energy sources. Science rarely moves from mystery to consensus in a single step. The black hole model gained strength because it could explain several facts at once: enormous luminosity, small source size, broad emission lines, rapidly moving gas, and the ability to remain active as long as material continued to fall inward. Yet quasars were so distant that they could not provide the cleanest first test. Astronomers needed a closer system where an invisible object could be weighed through the motion of a visible companion. That opportunity came from a part of the spectrum human eyes cannot see. Earth's atmosphere protects life by blocking most cosmic X-rays, but that protection also hides the high-energy universe from ground-based telescopes. To detect X-rays from space, instruments had to be carried above the atmosphere on balloons, sounding rockets, and eventually satellites. The early experiments were brief and difficult. A rocket might rise for only a few minutes, scan a narrow section of sky, and return with signals that had to be separated from detector noise and background radiation. In 1962, a team led by Riccardo Giacconi launched an instrument intended in part to search for fluorescent X-rays from the Moon. The lunar signal was not the great discovery. Instead, the detectors found a powerful source in the constellation Scorpius, later called Scorpius X1, along with the diffuse X-ray background. The universe had opened in a new color, and it was far more violent than visible astronomy had suggested. X-rays are produced in extremely hot environments, often where gas reaches millions of degrees. Compact objects were natural candidates because their gravity could accelerate infalling matter to enormous speeds and heat it through compression, shocks, and turbulence. A white dwarf could produce X-rays. A neutron star could produce even more. A black hole could power an intense X-ray source through its accretion disk without emitting from a surface at all. This created a new problem. A bright X-ray source alone was not proof of a black hole. The light came from the surrounding gas, and similar processes could occur around different kinds of compact stars. To make the case, astronomers needed to locate the source precisely, identify any visible companion, measure the orbit, and calculate the mass of the unseen object. The search accelerated after the launch of Uhuru in December 1970, the first satellite devoted to X-ray astronomy. Uhuru mapped hundreds of cosmic X-ray sources and showed that many changed in brightness. Among the most intriguing was Cygnus X1, located in the constellation Cygnus. Its X-ray output flickered rapidly, sometimes changing on timescales as short as fractions of a second. Rapid variation placed a limit on the size of the emitting region. An object cannot coordinate a change across a region faster than light can cross it. The source, therefore, had to be compact, not a vast cloud stretching across light years. It was producing tremendous energy in a space comparable in scale to a planet or smaller. Astronomers then connected the X-ray source with a bright blue supergiant star known as HDE 226868. The star appeared to move back and forth under the gravitational influence of an unseen companion. By studying shifts in its spectral lines, researchers could estimate its orbital motion and infer a minimum mass for the hidden object. The calculation was complicated by uncertainties in the visible star's own mass, the tilt of the orbit, and the behavior of the stellar wind. But the central result became increasingly difficult to avoid. The unseen companion was too massive to fit comfortably within the expected range of a white dwarf or neutron star. It did not produce the ordinary light of a massive star, yet it exerted a strong gravitational pull and sat at the center of an intense, compact X-ray source. A black hole was not the only imaginable explanation in the earliest discussions, but it was the one that required the fewest unsupported inventions. The likely picture was dramatic. HDE 226868 was losing gas through a powerful stellar wind. Some of that gas was captured by the invisible companion, heated to extreme temperatures as it spiraled inward, and made visible only during its final moments outside the horizon. Cygnus X1 was not seen as a circular black shape against the stars. It was reconstructed from motion, heat, timing, and missing light. Each clue alone left room for doubt. Together, they formed something stronger than a photograph, a physical argument. The orbit revealed hidden mass. The X-rays revealed infalling matter. The rapid flickering revealed a compact region. The absence of a visible object at the required mass ruled out ordinary stars. Later observations would refine the system's properties, and mass estimates would change as distances and models improved. But Cygnus X1 became the first widely accepted stellar mass black hole candidate. The word candidate mattered. Astronomy rarely proves the identity of a distant object by touching it or placing it in a laboratory. Confidence grows when different observations converge and rival explanations fail. In the case of Cygnus X1, there was no single frame in which the horizon appeared. There was, instead, a network of consequences that made sense if the unseen companion was a black hole. That method became the pattern for decades of research. Astronomers found other X-ray binaries, some persistent and others suddenly erupting when gas flooded their disks. They compared systems thought to contain neutron stars with those suspected of holding black holes. A neutron star has a surface, so falling matter can strike it and sometimes produce distinctive bursts or pulsations. A black hole has no material surface outside the horizon, so those signatures should be absent, though absence alone must always be interpreted carefully. Researchers studied disk temperatures, spectral states, jets, orbital motions, and the way X-ray brightness changed over time. None of these signs was a magical stamp reading black hole. Their power came from agreement. The universe was teaching astronomers how to detect an object by the behavior of everything around it. At the same time, quasars were transforming the scale of the problem. If accretion onto compact objects explained Cygnus X1, then the same basic engine, enlarged by millions or billions of solar masses, could explain the blazing centers of distant galaxies. The physics connected a nearby binary star to objects visible across most of the observable universe. Small black holes could form from dying stars. Enormous ones could dominate galactic nuclei. The horizon remained unseen, but black holes were no longer merely permitted by theory. They were becoming necessary to explain what telescopes were finding. And as astronomers followed the energy back toward its source, they were led from the death of individual stars to a far greater possibility. That immense black holes were not rare accidents hidden in space, but common occupants of the centers of galaxies, including our own. Once astronomers accepted that black holes could form from dying stars, a far larger mystery came into focus. The engines powering quasars seemed too energetic to be explained by anything merely stellar. The numbers forced the issue. Some quasars radiated more light than entire galaxies while producing that energy from regions smaller than the galaxies surrounding them. A source so compact and so luminous could not be powered by ordinary stars acting independently. Something at the center had to convert matter into radiation with extraordinary efficiency, and the most convincing candidate was a black hole containing millions or billions of times the mass of the Sun. These objects became known as supermassive black holes, although no one yet understood how nature could build them. A stellar black hole could be traced to the collapse of one massive star, but no single star could leave behind a remnant weighing 1 billion suns. Either smaller black holes had merged and grown over immense periods, or the early universe had found a faster route. The mystery deepened because quasars were not distributed randomly through cosmic time. many were seen at enormous distances, meaning their light had begun traveling when the universe was much younger. Some gigantic black holes were already feeding intensely less than 1 billion years after the Big Bang. That gave them surprisingly little time to grow, especially if their feeding rate was limited by the pressure of the radiation they produced. A black hole consuming gas creates light, but that light can push incoming matter away. Growth therefore contains its own resistance. To reach billions of solar masses so early, the first seeds may have been unusually massive, may have experienced episodes of rapid feeding, or may have grown through repeated mergers in dense young galaxies. Each path remains plausible in some environments, and the real history may involve several of them rather than one universal solution. The evidence that such monsters occupied galactic centers did not come only from quasars. Astronomers began measuring the motion of stars and gas near the centers of nearby galaxies, looking for speeds that could not be explained by visible matter alone. If stars near a galactic nucleus were moving hundreds or thousands of miles per second, something extremely massive had to be holding them in orbit. In the galaxy M87, a giant elliptical system at the heart of the Virgo cluster, observations revealed gas rotating rapidly around a central region containing billions of solar masses. The mass was concentrated into a volume too small to be easily explained by an ordinary cluster of stars. In other galaxies, similar patterns emerged. The more carefully astronomers looked, the more often they found evidence for enormous dark masses in the middle. The idea that only unusual, violently active galaxies contained supermassive black holes gradually gave way to a more surprising possibility. Perhaps most large galaxies had one, but many were quiet. A black hole without a steady supply of gas can become nearly invisible. Its existence may be revealed only by the orbits of nearby stars, the motion of gas, or a sudden flare when some new material wanders too close. A quasar, in this view, is not a special type of permanent object. It is a phase in the life of a galaxy, a period when the central black hole is feeding rapidly enough to turn the nucleus into a cosmic beacon. When the fuel supply fades, the same black hole can remain dormant for millions of years. This meant that the difference between a blazing quasar and an apparently ordinary galaxy might not be the presence of a black hole, but whether that black hole was being fed. The question soon became personal, because our own Milky Way appeared to contain one. The center of the galaxy lies roughly 26,000 light-years away in the direction of Sagittarius, hidden behind thick clouds of interstellar dust. Visible light cannot pass cleanly through that material, so the galactic center looks dark to ordinary telescopes. Radio waves and infrared light, however, can penetrate much of the dust. In the 1930s, Karl Jansky detected radio emission coming from the direction of the Milky Way's center, helping launch the field of radio astronomy. Decades later, astronomers identified a compact radio source there and named it Sagittarius A star, pronounced Sagittarius A star. The source was unusual, but radio emission alone could not prove that it was a black hole. The decisive evidence would come from stars moving around it. Beginning in the 1990s, teams led by Reinhard Genzel in Europe and Andrea Ghez in the United States used increasingly powerful infrared telescopes to follow individual stars in the crowded central region. This was an extraordinary observational challenge. Earth's atmosphere blurs starlight. The target area is packed with overlapping sources, and the stars needed to be tracked with great precision over many years. Advances in adaptive optics allowed telescopes to correct for atmospheric distortion, sharpening the view enough to measure stellar positions repeatedly. What emerged was one of the most compelling gravitational maps ever made. Stars near Sagittarius A star were racing around an invisible point. Some moved so quickly that their positions changed noticeably from year to year. One star, now commonly called S2 or S0-2, depending on the research group, completed an orbit in about 16 years. At its closest approach, it passed within roughly 17 light hours of the central object and moved at several % of the speed of light. Its orbit was highly elongated, accelerating dramatically as it swept near the center before climbing outward again. By tracing that path, astronomers could weigh the unseen mass. The result was about 4 million suns packed into a region smaller than our solar system. A dense cluster of dark stars, neutron stars, or stellar remnants might imitate some of this gravity, but such a cluster would be difficult to keep stable. Its members would collide, scatter one another, or merge on timescales much shorter than the age of the galaxy. The simplest explanation, and by far the strongest supported one, was a supermassive black hole. The orbits also offered a new arena for testing general relativity. As S2 passed close to Sagittarius A star, its light experienced gravitational redshift, and its orbit showed a subtle relativistic shift in orientation rather than closing into a perfect ellipse. These measurements matched Einstein's theory within current observational limits. The galactic center was no longer merely a place where an invisible mass appeared to sit. It had become a laboratory where gravity could be tested under conditions impossible to reproduce on Earth. Yet Sagittarius A star was surprisingly dim. With 4 million solar masses, it could, in principle, release enormous energy if gas were falling into it rapidly. But it currently consumes very little compared with active galactic nuclei. The Milky Way therefore contains a sleeping monster, not a quasar. This contrast revealed something important about the history of galaxies. Central black holes can pass through active and quiet periods depending on the flow of matter around them. A galaxy merger may drive gas inward and awaken the nucleus. A star passing too close may be torn apart, producing a temporary flare known as a tidal disruption event. Dense clouds can feed the black hole unevenly. After the material is exhausted or blown away, the nucleus can fade again. Black holes are not simply passive objects waiting at galactic centers. When active, they can influence regions far beyond their horizons. Accretion disks generate intense radiation. Magnetic fields near rotating black holes can help launch narrow jets of plasma that extend thousands or even millions of light years. These jets do not emerge from inside the horizon. They are produced by matter and fields in the surrounding environment, possibly drawing energy from the black hole's rotation. They can heat gas throughout a galaxy cluster, stir surrounding material, and reduce the amount of cold gas available to form new stars. This process, broadly called feedback, may help explain why the growth of galaxies and the growth of their central black holes appear connected. Astronomers found correlations between the mass of a central black hole and properties of the galaxy's central bulge, including the speeds of its stars. The relationship was too consistent to dismiss as coincidence, yet its direction was unclear. Did galaxies determine how much their black holes could grow? Or did black holes regulate the galaxies around them? Perhaps both developed together through repeated cycles of feeding, star formation, mergers, and feedback. A black hole is tiny compared with its host galaxy, often occupying a region vastly smaller than the galactic structure it may influence. That such a compact object could help shape the evolution of billions of stars is one of the most remarkable changes in how astronomy came to understand galaxies. Still, the black hole is not the sole architect. Dark matter, gas supply, stellar explosions, environment, and merger history all contribute. Feedback is powerful, but its exact strength and behavior vary between systems, and simulations continue to test how these processes operate across cosmic time. By the early 21st century, the evidence had transformed the black hole from a rare stellar grave into a central figure in galactic history. Supermassive black holes appeared to be common, perhaps nearly universal, in large galaxies. They could sleep quietly for ages, awaken as quasars, launch immense jets, and alter the conditions under which new stars formed. Yet the greatest puzzle remained untouched. Astronomers could measure their mass, observe their surroundings, and follow stars orbiting just beyond their reach. But the horizon itself remained hidden below the limits of every telescope. The monster at the heart of a galaxy could be weighed with astonishing precision, while its defining boundary had never been seen. That would eventually change. But before humanity could build a telescope large enough to resolve the shadow of a black hole, physics delivered an even stranger revelation. These objects might not be perfectly black, and the information they swallowed might threaten the deepest rules of the quantum world. The crisis began with a question that sounded almost trivial. What happens to disorder when something falls into a black hole? In ordinary physics, disorder is measured by entropy, a quantity that does not usually decrease in an isolated system. Burn a book, and the words vanish from view, but the physical information is not truly erased. It is scattered into ash, heat, light, and motion. A black hole seemed different. Drop the same book across the horizon, and from the outside, every detail about its pages, ink, and arrangement appeared to disappear, leaving behind only a slight increase in the black hole's mass, spin, or charge. If all of that structure were simply removed from the accessible universe, then entropy outside the black hole could decrease, threatening the second law of thermodynamics, one of the most reliable principles in science. In the early 1970s, a young physicist named Jacob Bekenstein took this problem seriously. He proposed that a black hole must carry entropy of its own, and that the entropy should be connected not to the volume inside the horizon, but to the area of the horizon itself. The idea was radical. Entropy normally counts the number of hidden microscopic arrangements that can produce the same large-scale appearance. Yet a black hole seemed to have no visible internal details at all. Its exterior could be described by only a few quantities: What hidden states could possibly be counted? Bekenstein did not yet know, but he argued that the horizon area behaved too much like entropy to be ignored. When matter fell in, the area tended to increase. When two black holes merged, the final horizon was larger than the combined areas in a way that echoed the one-way growth of entropy. The resemblance was strengthened by mathematical work showing that black holes followed laws strangely similar to the laws of thermodynamics. Surface gravity played a role resembling temperature. Horizon area resembled entropy. Mass resembled energy. At first, many physicists treated these parallels as elegant analogies and nothing more. A true temperature would mean a black hole could radiate, and that seemed impossible by definition. Nothing crossed outward through the horizon. If black holes emitted nothing, then their temperature had to be zero. And if their temperature was zero, Bekenstein's interpretation appeared to be only symbolic. Stephen Hawking initially opposed the idea for much the same reason. Then, he tried to prove it wrong. In 1974, Hawking studied quantum fields near a black hole and found that the calculation refused to preserve the darkness everyone expected. To a distant observer, the black hole behaved as though it emitted thermal radiation. The result became known as Hawking radiation, and it changed the meaning of a black hole more deeply than almost any discovery since general relativity itself. The explanation is often reduced to a picture of particle pairs appearing at the horizon, with one falling inward and the other escaping. That image can be useful as a rough intuition, but it is not the full calculation and can easily mislead. The deeper idea is that empty space in quantum theory is not truly empty. Quantum fields remain present, and the meaning of a particle depends partly on how an observer moves through spacetime. When a horizon forms, modes of the field that seem empty to a falling observer can appear as a stream of particles to someone far away. The radiation does not need to climb from inside the black hole. It arises from the behavior of quantum fields in the curved region outside and around the horizon. The temperature is extraordinarily low for an astrophysical black hole. A black hole with the mass of the Sun would be far colder than the cosmic microwave background that fills the universe, so it would currently absorb more energy than it emits. Larger black holes are colder still. Only very small black holes would radiate strongly, and no confirmed population of such objects is known. The effect is therefore not something astronomers expect to observe easily from ordinary stellar or supermassive black holes. Yet its theoretical importance is enormous. Radiation carries energy away. If the black hole has no external source of matter to replace that energy, its mass must slowly decrease. Over a timescale vastly longer than the current age of the universe, it could evaporate. As it shrinks, its temperature would rise, making the final stages progressively faster and more energetic, though exactly what happens at the very end may require physics beyond the theories now available. This picture transformed black holes from eternal prisons into objects with lifetimes. It also completed the link between gravity, quantum theory, and thermodynamics. The horizon had a real temperature. Its area represented a genuine entropy. The proportionality was astonishing. Black hole entropy depends on the area measured in units built from gravity, quantum mechanics, and the speed of light. That combination suggested that the formula was not merely about black holes. It might be revealing something fundamental about the quantum structure of spacetime. The strange emphasis on area rather than volume led to a deeper suspicion. Perhaps the information contained in a region of space can, in some sense, be represented on its boundary. This idea would later grow into the holographic principle, though its precise meaning depends on the theoretical setting and should not be treated as a proven description of every physical situation. Still, black holes had exposed a clue that ordinary matter had hidden. The capacity of space to hold information may be limited by surface area, not by the amount of volume available inside. But Hawking's result solved one problem only by creating a more dangerous one. The radiation he derived was thermal. It depended on broad properties such as the black hole's mass, not on the detailed identity of the matter that formed it. Imagine building one black hole from stars and another from clouds of radiation, arranging them so both have the same mass, spin, and charge. In the classical description, their exteriors become indistinguishable. If both later evaporate into the same featureless thermal radiation, the differences in their beginnings appear to vanish forever. Quantum mechanics does not normally allow that. A quantum state can evolve into another state, and its information may become hopelessly scrambled, but it is not supposed to be fundamentally destroyed. A burned book is difficult to reconstruct, yet in principle, the correlations among its particles still contain traces of the original text. Complete black hole evaporation seemed to offer no such traces. The initial state could be rich with detail, while the final radiation carried only a temperature. Many distinct pasts would collapse into the same future, making the laws of physics unable to run consistently backward even in principle. This became the black hole information paradox. For years, Hawking argued that information might truly be lost, forcing quantum mechanics to be modified. Other physicists, including John Preskill and Gerard 't Hooft, believed the information had to survive, even if no one could explain how. The debate was not about whether a person could practically retrieve a diary thrown into a black hole. It was about whether nature preserves the distinctions between possible quantum states at the deepest level. If it does not, probabilities in quantum theory may stop adding up in the usual way. If it does, then Hawking's apparently thermal radiation must hide correlations that the original calculation did not reveal. One possibility is that information escapes gradually, encoded in extremely subtle relationships among the emitted quanta. The radiation could look thermal when examined piece by piece, while still carrying the full history in its collective pattern, much as random-looking fragments can conceal a message when arranged correctly. This idea gained support through developments in quantum gravity and the study of so-called page curves, which describe how the entanglement entropy of the radiation should change if evaporation preserves information. In an information-preserving process, the radiation initially appears increasingly mixed, but after a certain point, the hidden correlations begin to emerge, and the total entropy eventually falls back toward zero when evaporation ends. Recent theoretical calculations, using methods involving quantum extremal surfaces and replica wormholes, have reproduced this expected curve in simplified gravitational models. These results are widely viewed as important evidence that information is not destroyed, but they do not yet provide a complete, universally accepted, microscopic description of how information escapes from a realistic, astrophysical black hole. The paradox becomes sharper near the horizon, because general relativity says a freely falling observer should experience nothing special at a sufficiently large horizon, while quantum arguments about information can seem to require violent changes there. This tension inspired the firewall proposal, which suggested that the horizon might become a high-energy barrier, destroying anything that crosses it. The idea preserves certain quantum principles, but sacrifices the smooth horizon predicted by relativity. Many physicists find that cost severe, and no consensus has formed around firewalls. Other proposals imagine that the interior is replaced by a complicated quantum structure, as in some versions of the fuzzball idea from string theory. Some suggest that black holes possess subtle, soft hair, additional low-energy features that may record information, though it remains debated whether such effects are sufficient to solve the full paradox. Another possibility is that space-time itself is emergent, built from deeper patterns of quantum entanglement, making the separation between inside and outside less fundamental than it appears. In that view, the paradox may arise because classical geometry divides reality too sharply. There are also more speculative possibilities. A tiny remnant could remain after evaporation and store the information, or information could pass into another region of spacetime. These ideas face serious challenges, including questions about stability, energy, and whether an object with limited size could hold an unlimited history. None has been confirmed experimentally. What makes the paradox so powerful is that every proposed solution seems to demand a sacrifice. Preserve a smooth horizon, and the information may appear trapped. Preserve ordinary quantum evolution, and the horizon may need new structure. Allow information to escape, and one must explain how it avoids violating the apparent locality of physics. Let it disappear, and quantum mechanics itself must be altered. Black holes have therefore become less like isolated astronomical objects and more like judges testing the consistency of the laws around them. Their temperature is almost unimaginably faint, but the implication burns through modern physics. Somewhere in the relation between horizon area, quantum entanglement, and evaporation may lie the missing theory that unites gravity with the quantum world. For now, no telescope can watch a stellar black hole evaporate, and no experiment can directly inspect the information crossing a distant horizon. The argument continues through equations, models, and carefully constructed thought experiments. Yet the question is no longer whether black holes are completely dark. The deeper question is whether they are allowed to forget, and if they are not, how the universe returns what seemed lost. At 5:51 in the morning on September 14th, 2015, a disturbance passed through Earth that no human being could feel. It did not shake buildings, stir the ocean, or move the needle of an ordinary seismograph. The change was far smaller than an atomic nucleus, yet two enormous instruments in the United States recorded it within milliseconds of each other. At the Livingston Observatory in Louisiana, laser beams traveling through two 4-kilometer vacuum tunnels shifted in a precise pattern. A moment later, the same pattern appeared at the Hanford Observatory in Washington State. The signal lasted only a fraction of a second. It began as a low, slow oscillation, climbed rapidly in pitch and strength, and ended in a sudden fade. Converted into sound, it resembled a short, upward chirp. Behind that modest noise lay an event of almost unimaginable violence. Two black holes had spiraled together, collided, and become one. For the first time, humanity had detected black holes not through the stars orbiting them, the gas heating around them, or the light emitted before matter disappeared, but through ripples moving directly across the fabric of space-time. Einstein had predicted such ripples in 1916, only months after completing general relativity. According to his equations, accelerating masses could disturb space-time and send waves outward at the speed of light, much as a moving object creates waves across water. The comparison is useful only to a point. Gravitational waves do not travel through space-time as sound travels through air. They are changing space-time itself, alternately stretching one direction while squeezing another. Any object in their path changes shape by an almost imperceptible amount. The stronger the acceleration and the larger the masses, the more powerful the waves can be. But by the time they cross astronomical distances and reach Earth, the distortion is usually vanishingly small. Einstein himself doubted that such signals would ever be measured. Even if the waves were real, the available technology seemed hopelessly inadequate. For decades, they remained one of general relativity's most elusive predictions. The first serious experimental attempts came from Joseph Weber, an American physicist who built massive aluminum cylinders during the 1960s. His idea was that a passing gravitational wave might make the metal ring slightly, like an enormous bell responding to a distant strike. Weber eventually announced that he had detected signals, creating excitement and controversy, but other groups could not reproduce his results. His claimed detections were not accepted, yet the effort was not meaningless. Weber helped transform gravitational waves from a theoretical curiosity into an experimental target. He had shown that scientists were willing to build machines designed to listen for motions no one had ever confirmed. Stronger evidence arrived indirectly in the 1970s, when Russell Hulse and Joseph Taylor discovered a binary system containing two dense stellar remnants, one of them a pulsar that emitted radio pulses with remarkable regularity. The two stars orbited each other in less than 8 hours. Over time, their orbit gradually shrank. The rate matched the energy loss predicted if the system were emitting gravitational waves. It was not a direct detection. The waves themselves were not measured as they passed Earth, but the decaying orbit showed that energy was leaving exactly as Einstein's theory said it should. The universe was almost certainly producing gravitational waves. The challenge was building an instrument sensitive enough to catch one. The answer would not come from metal bars, but from light. A laser interferometer divides a laser beam and sends the two parts down perpendicular tunnels. Mirrors reflect them back, and the beams are recombined. If the two paths remain exactly the same length, the light waves return in a predictable relationship. A gravitational wave passing through the detector stretches one arm while compressing the other, changing the distance traveled by the beams and creating a detectable interference pattern. The principle sounds straightforward. The engineering was not. The mirrors had to be isolated from earthquakes, trucks, ocean waves, wind, thermal motion, and countless smaller disturbances. The vacuum tunnels had to remain extraordinarily empty. The lasers had to be stable. The mirrors, weighing tens of kilograms, had to hang almost motionless while the instrument searched for a relative length change of roughly 1 part in 10 to the 21st. Over a 4-kilometer arm, that meant measuring a displacement thousands of times smaller than a proton. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was built around this impossible demand. Its first observing runs began in the early 2000s, and found no confirmed signals. That silence was not failure in the ordinary sense. It allowed engineers to understand noise, refine the detectors, and prepare for a much more sensitive upgrade called Advanced LIGO. By September 2015, the improved instruments were being tested before their official observing run. Then the signal arrived. At first, the researchers had to consider the possibility that it was artificial. The collaboration sometimes inserted hidden test signals into the data to evaluate whether the analysis teams could identify them. Equipment glitches could also mimic unusual patterns. But this event had not been planted. Its form appeared in both detectors, with the timing expected for something crossing Earth at the speed of light. It matched the waveform predicted for two massive compact objects spiraling together. The signal was named GW150914, gravitational wave, detected on September 14, 2015. By comparing the observed pattern with numerical models based on general relativity, scientists reconstructed the final moments of the distant system. One black hole contained about 36 times the mass of the Sun, the other about 29. For millions, or perhaps billions of years, they may have orbited one another while gradually losing energy through gravitational radiation. Most of that long history was quiet from Earth's perspective. The orbital decay accelerated only near the end. During the final fraction of a second, the black holes circled each other dozens of times per second, moving at a significant fraction of the speed of light. Their horizons distorted as the two objects approached, until they merged into a single, violently disturbed black hole. The newborn object then settled into a stable form, releasing a final pattern known as ringdown, like a struck bell losing its vibration. The final black hole had about 62 solar masses. Roughly 3 suns' worth of mass had vanished from the material accounting, but it had not been destroyed. It had been converted into gravitational wave energy, according to Einstein's relation between mass and energy. For a brief moment, the collision released more power than all the stars in the observable universe combined, though almost all of it traveled as gravitational waves rather than visible light. The event occurred about 1.3 billion light-years away, meaning the waves began their journey when complex life on Earth was still far in the future. They crossed intergalactic space, passed through galaxies and clouds without being significantly absorbed, and finally altered the lengths of 2 pairs of tunnels by an almost unthinkably small amount. The public announcement came on February 11, 2016, after months of checking, analysis, and internal scrutiny. The result did more than confirm that gravitational waves existed. It proved that binary black holes could form, survive, and merge within the lifetime of the universe. Before this detection, astronomers knew of stellar mass black holes, mostly through systems where a black hole interacted with a visible companion. Quiet pairs of black holes, with no glowing gas and no ordinary star nearby, could remain nearly impossible to see. LIGO had opened a channel capable of finding them precisely because they were dark. The waveform carried information about their masses, spins, orbital motion, and distance, In effect, the collision wrote its own history into spacetime, and the detectors read that history from the changing separation of mirrors. The discovery also revealed that black holes of several tens of solar masses were more common than many researchers had expected. Later detections expanded the population, uncovering objects with a wide range of masses and spins. Some may have formed from massive stars in environments with relatively few heavy elements, allowing the stars to lose less mass before collapse. Others may have paired through ordinary binary evolution, while some could have met inside dense star clusters, where repeated gravitational encounters bring compact objects together. The contribution of each formation pathway remains under investigation. Gravitational wave astronomy does not merely count black holes. It offers clues about how generations of stars lived and died in places too distant to observe individually. Each merger also tests general relativity under conditions of extreme gravity and rapid motion. So far, the observed waveforms have agreed remarkably well with the theory, though researchers continue searching for subtle deviations that might reveal new physics. The ring-down is especially valuable because its frequencies depend on the properties of the final black hole. More sensitive observations may allow scientists to test whether the remnant behaves exactly like the black holes predicted by general relativity, or whether hidden structures leave faint traces. No confirmed deviation has yet forced a replacement for Einstein's description, but the question remains open, because every improvement in detector sensitivity creates a stricter test. What began as one chirp has become a new way of studying the universe. LIGO was joined by Virgo in Italy and later CAGRA in Japan, improving scientists' ability to locate sources and compare signals across multiple detectors. Future observatories on Earth are expected to hear weaker and more distant collisions, while planned space-based detectors could follow massive black holes orbiting at lower frequencies long before they merge. The meaning of seen had changed. Astronomers had spent centuries collecting light, but black holes could now announce themselves through gravity alone. They no longer needed a bright companion, a hot disk, or a jet. Two invisible objects could collide in complete darkness and still send a measurable message across a billion years of space. Yet even this triumph stopped outside the horizon. The waves revealed the black hole's motion and merger, not the events hidden within them. Humanity had heard their final dance, but had still never resolved the shadow cast by the boundary itself. To do that, astronomers would need to turn the entire Earth into a single telescope and attempt something that once sounded even more impossible: constructing an image of the darkness around a black hole. For decades, the horizon remained just beyond the reach of every telescope. Not because black holes were too dim in the ordinary sense, but because the region astronomers needed to resolve was unimaginably small on the sky. Even a supermassive black hole could appear narrower than a grain of sand seen from thousands of miles away. The challenge was not simply gathering more light. It was sharpening vision until a telescope could distinguish structures near the point where gravity bends light into loops and sends some of it back toward the universe. Two black holes offered the best opportunities. One was Sagittarius A star, the roughly 4 million solar mass object at the center of the Milky Way. The other lay much farther away in M87, a giant elliptical galaxy about 55 million light-years from Earth. The black hole in M87 was more distant, but it was also more than 1,000 times as massive as Sagittarius A star, giving its shadow a similar apparent size in the sky. It also changed more slowly, an advantage that would become crucial. The telescope needed to see either object did not exist as a single machine, and building a conventional dish large enough was impossible. So astronomers used a different idea. Instead of constructing one telescope the size of a planet, they would persuade observatories across Earth to behave as though such a telescope already existed. The project became known as the Event Horizon Telescope, or EHT, a global network of radio observatories linked through a technique called Very Long Baseline Interferometry. The name sounds technical, but the principle is almost cinematic. Radio waves from the same distant source arrive at separated telescopes at slightly different moments. If those arrival times are recorded with extreme precision, the observations can later be combined, allowing the distance between the telescopes to act like the width of a much larger virtual instrument. A dish in Hawaii, another in Spain, another in Chile, another near the South Pole. Each becomes one piece of an Earth-sized eye. The farther apart the stations, the finer the detail the network can resolve. But this planet-sized telescope had no shared mirror and no cable connecting its pieces in real time. Every location had to record the incoming radio waves independently, using hydrogen maser atomic clocks accurate enough to keep the data aligned to a tiny fraction of a second. Even a small timing error could blur the result into meaninglessness. The observations were made at a wavelength of about 1.3 millimeters, short enough to provide extraordinary resolution, but long enough to pass through much of the gas and dust that would hide the region at other wavelengths. At this frequency, Earth's atmosphere becomes part of the problem. Water vapor absorbs and distorts the signal, so the telescopes had to sit in dry, high places whenever possible, on volcanic peaks, in deserts, and on the Antarctic ice. Every station also needed clear weather at the same time. The black hole might be ready, but if clouds or humidity interfered at several observatories, the planet-sized telescope would lose pieces of its vision. In April 2017, after years of preparation, the network observed several targets over a series of nights. M87 star, the name used for the compact object at the center of M87, was among them. The campaign required a rare alignment of technology, weather, human coordination, and geography. Telescopes across multiple continents turned toward the same invisible region. Their receivers collected not a normal photograph, but enormous streams of radio data, preserving the subtle relationships between waves arriving at each site. The amount of information was so large that it could not simply be sent over the internet. Hard drives had to be physically transported to central processing facilities, where specialized supercomputers called correlators compared the recordings and reconstructed the interference patterns. Data from the South Pole could not even be shipped until the Antarctic winter ended and flights resumed. The image that would eventually circle the world therefore began as boxes of drives traveling across the planet, each carrying fragments of a signal that had already crossed 55 million years of space. Combining those fragments was only the beginning. An interferometer does not fill in every point of an image. It samples portions of the spatial information, leaving gaps that must be handled carefully. Different imaging methods can sometimes produce different-looking results when data are incomplete. So the collaboration divided researchers into independent teams. They worked with separate algorithms and were discouraged from comparing their images too early. This was designed to prevent one group's expectations from shaping another group's result. They also tested their methods on simulated data, asking whether the software could recover known structures without inventing features. Calibration errors, atmospheric effects, instrument behavior, and possible biases all had to be examined. The goal was not to create the most dramatic picture. It was to determine which features remained stable no matter which reasonable reconstruction method was used. Again and again, the same basic form emerged: a bright, uneven ring surrounding a dark central region. On April 10, 2019, the collaboration revealed that image to the world. It seemed almost primitive at first glance: a soft orange ring, brighter along one side, wrapped around a circular darkness. Yet the apparent simplicity concealed the scale of what had been achieved. The picture was not a direct photograph of the event horizon, and the dark center was not an empty hole, visible like a cave entrance. The radio glow came from extremely hot plasma moving around the black hole. Gravity bent the paths of photons, causing light from different parts of the flow to curve around the object before reaching Earth. Some rays could travel partway around the black hole, and in ideal conditions, even circle it more than once, though the finest structures created by these repeated paths were not resolved in the first image. Other rays crossed too close and were captured. The result was a dark depression larger than the horizon itself, the black hole's shadow. This shadow was created by the combined effects of light bending and photon capture, a silhouette written into the surrounding radiation by the geometry of spacetime. The brighter lower portion of the ring carried another clue. Material in the emitting region was moving at a significant fraction of the speed of light. Radiation from plasma moving toward Earth was enhanced by relativistic beaming, while radiation from material moving away appeared dimmer. The asymmetry did not mean the black hole was glowing more strongly on one side. It reflected the motion of matter around it and the way relativity alters the light received by a distant observer. The size of the ring was also critical. It matched, within observational uncertainty, the scale expected for a black hole of roughly 6.5 billion solar masses under general relativity. A concept once hidden inside equations had produced a measurable outline in the sky. The image did not prove every aspect of black hole theory, nor did it expose the singularity or reveal what happens beyond the horizon. It could not show matter crossing the boundary because light from inside cannot return. It did not settle the information paradox, confirm a theory of quantum gravity, or eliminate every imaginable alternative compact object. What it did was far more disciplined. It showed that the region around M87 star had the size and appearance expected from an extremely massive black hole surrounded by hot plasma. Alternative models would have to reproduce not one vague darkness, but a specific ring, scale, shape, and gravitationally lensed structure. The image also gave astronomers a new way to test how matter and magnetic fields behave near a horizon. In 2021, the collaboration released polarized light observations of M87 star, revealing patterns linked to magnetic fields in the emitting plasma. These fields are likely important in controlling how gas falls inward and how the galaxy's enormous jet is launched. M87 produces a narrow stream of energetic particles extending far beyond its central region, and one of the deepest goals of future observations is to connect what happens near the horizon with the formation of that jet. The black hole itself does not shoot matter from inside. Instead, magnetic fields in the surrounding disk and rotating spacetime may redirect energy outward before material crosses the point of no return. The exact details remain an active area of study, but the EHT had begun turning the edge of a black hole into an observable laboratory. Then came the harder target. Sagittarius A star is much closer than M87 star, but its lower mass makes matter orbit near it far more quickly. During a single night of observation, the plasma can change significantly. Imaging M87 star was like photographing a mountain that remained mostly still. Imaging Sagittarius A star was more like attempting a long exposure picture of a restless animal that changed shape while the camera was open. The collaboration had to develop methods that accounted for this rapid variability, rather than assuming the source remained fixed. On May 12, 2022, the first image of Sagittarius A star was released. It again showed a bright ring surrounding a dark central region, although the published picture represented an average of many possible structures consistent with the changing data. Its scale agreed with the mass already measured from nearby stellar orbits. This was a remarkable convergence of independent methods. For years, astronomers had watched stars race around an unseen central mass and concluded that a black hole was the most convincing explanation. Now, radio observations had resolved a shadow of the expected size around that same location. One method followed the gravitational influence across years and distances measured in light hours. The other examined glowing plasma on scales close to the horizon. Both pointed toward the same object. The two images also revealed how misleading size can be in astronomy. M87 star is vastly more massive than Sagittarius A star, yet their shadows appear roughly comparable in angular size because the Milky Way's center is so much closer. M87 star changes slowly enough to offer a steadier portrait, while Sagittarius A star exposes a more dynamic environment. Together, they are not duplicate pictures, but complementary experiments, one showing the calm scale of a gigantic galactic engine, and the other showing the restless heart of the galaxy we inhabit. The first images did not end the search, they changed its form. Researchers now aim to add more telescopes, improve resolution, observe at additional frequencies, and eventually create time-resolved sequences showing plasma moving around a black hole, rather than only a reconstructed still image. Future networks may reveal finer rings produced by photons taking multiple paths around the horizon, sharpen measurements of black hole spin, and test whether shadows match general relativity with increasing precision. Yet, even the clearest future image will remain an image of the boundary's influence, not a view into the interior. That limitation is not a failure of technology. It is the defining physical fact of the object. Humanity had finally constructed a picture of darkness, but the darkness itself still refused to speak. The history of black holes had reached a point earlier generations could hardly have imagined. They had been predicted, weighed, heard in collision, and outlined against their own glowing surroundings. What remained was no longer the question of whether they existed. It was the deeper question of what these objects could reveal about the origin of galaxies, the first structures in the universe, the nature of information, and the laws that may replace our current theories at the edge of spacetime. The most important change in black hole science is that existence is no longer the mystery. The mystery is, what kind of universe can produce such a wide range of them? How quickly they can grow? What remains hidden behind their horizons? And whether the laws that describe them can survive when gravity and quantum mechanics are forced into the same room. The next chapter of the story is therefore not centered on one object or one discovery. It is unfolding across observatories, supercomputers, underground detectors, and mathematical theories that do not yet agree on what spacetime is made of. One of the first unresolved problems begins near the dawn of the universe. Astronomers have found extremely distant quasars powered by black holes already containing hundreds of millions or even billions of solar masses when the cosmos was still young. Their light has traveled for more than 13 billion years, allowing telescopes to see them as they existed only several hundred million years after the Big Bang. The puzzle is not simply that they are large. It is that ordinary growth may not have had enough time to make them so large. A black hole feeding from a disk cannot always consume material as quickly as gravity might suggest, because the radiation generated by infalling gas pushes outward and can limit the supply. Beginning with a black hole left by a single massive star, then growing steadily under familiar conditions, may struggle to produce the largest early quasars within the available time. That has led researchers to consider heavier starting points. Some of the first stars may have been far more massive than most stars born today, leaving behind unusually large remnants. In another possibility, enormous clouds of primordial gas may have collapsed almost directly into black holes weighing thousands or tens of thousands of suns, avoiding the ordinary stellar stage. Dense clusters could also have produced repeated collisions and mergers, building a massive seed before the surrounding galaxy fully matured. None of these routes has been established as the single explanation, and the early universe may have used several at once. Future observations must determine not only how many ancient black holes existed, but what kinds of galaxies surrounded them, how rapidly they were feeding, and whether their growth occurred before, during, or after the formation of the first large stellar systems. Between stellar remnants and supermassive giants lies another uncertain territory: intermediate mass black holes. These hypothetical or partially observed objects would weigh hundreds to hundreds of thousands of solar masses, filling the enormous gap between the known populations. Evidence for candidates has appeared in dense star clusters, dwarf galaxies, unusual X-ray sources, and gravitational wave events, but many cases remain difficult to interpret. A compact cluster of smaller objects can sometimes imitate the gravitational influence of one larger black hole. Bright X-ray sources can be affected by beaming, making them appear more powerful than they truly are. Even a merger that seems to create an intermediate mass remnant may leave questions about the masses of the original objects and the environment where they formed. Establishing a clear population would matter, because these black holes may preserve the missing stages in the growth of galactic centers. If they are common in small galaxies, they could be ancient seeds that never gained enough fuel to become supermassive. If they are found mainly in dense star clusters, repeated mergers may be an important route to their formation. If they are rare, then the universe may leap from stellar remnants to massive seeds through a process not yet fully understood. Another possibility reaches even farther back, to a time before stars existed at all. Primordial black holes may have formed from unusually dense regions in the early universe, when matter and radiation were distributed with tiny variations that later grew into galaxies. If some regions were dense enough, they might have collapsed directly under their own gravity. Such objects could, in theory, span a wide range of masses, depending on when and how they formed. They have been proposed as a possible contributor to dark matter, the invisible substance inferred from the motions of galaxies and the structure of the cosmos. But this remains a hypothesis, not a confirmed explanation. Observations have placed strong limits on how abundant primordial black holes can be across many mass ranges. Gravitational lensing surveys, cosmic background measurements, dynamical effects, and searches for evaporation signatures have all narrowed the possibilities. Certain windows may remain open, and even a small population would carry valuable information about conditions in the first fractions of a second after the Big Bang. Finding one would not merely add another type of black hole. It would reveal that gravity was already creating collapsed objects before the first stars had begun to shine. The horizons of known black holes also offer a place to test whether general relativity remains exact under the strongest accessible conditions. So far, observations have repeatedly matched Einstein's predictions, but agreement does not end the search. Every theory has a domain where it may eventually fail, and gravity near a horizon provides one of the few environments where tiny deviations could become measurable. Researchers study the shapes of shadows, the motion of hot plasma, the frequencies produced when merged black holes settle, and the paths of stars orbiting close to galactic centers. A black hole that differs slightly from the expected rotating solution might leave an altered ring-down signal after a merger, or distort the orbit of nearby matter in a characteristic way. The difficulty is separating a true failure of gravity theory from the complicated behavior of gas, magnetic fields, turbulence, and imperfect instruments. A shadow that appears unusual may reflect the plasma surrounding the object rather than a different spacetime. A gravitational wave signal that departs from a model may come from an unexpected orbit or an incomplete understanding of the detector noise. Strong claims, therefore, require several independent lines of evidence. The goal is not to overthrow relativity for the sake of novelty, but to press it until nature reveals whether it is the final description of gravity or an exceptionally accurate approximation to something deeper. That deeper theory is likely to become unavoidable at the center of the problem. General relativity treats spacetime as a smooth geometry. Quantum mechanics describes nature through fields, probabilities, and discrete interactions. Both theories are extraordinarily successful, yet their usual forms cannot be applied together without trouble under the most extreme conditions. The classical singularity inside a black hole is therefore often interpreted not as a literal prediction that nature contains an infinitely dense point, but as a warning that the theory has reached beyond its proper domain. What replaces that singularity is unknown. In some approaches, spacetime may possess a smallest meaningful scale, preventing matter from being compressed without limit. In others, the interior could be described through quantum states that have no simple geometric interpretation. A collapse might lead to a bounce, a highly compressed core, a network of quantum geometry, or something that cannot be represented using familiar ideas of location and time. These possibilities are speculative and difficult to test because the horizon blocks direct communication from the interior. Yet, they are not completely detached from observation. The way black holes merge, ring down, or perhaps evaporate could contain indirect traces of their quantum structure. Some models predict faint echoes following the main gravitational wave signal, although no widely accepted detection has established such echoes. Others suggest that the horizon itself may be replaced or modified by quantum effects. Any confirmed departure would be revolutionary, but current evidence does not require abandoning the classical horizon. The problem is made even stranger by the growing possibility that spacetime may not be fundamental at all. Several lines of theoretical work suggest that geometry could emerge from patterns of quantum entanglement, much as temperature emerges from the collective behavior of particles, even though no single particle possesses a temperature by itself. In this view, the smooth space around a black hole might be a large-scale description of deeper quantum relationships. The connection between horizon area and entropy becomes especially suggestive because it implies that the amount of information associated with a region may scale with its boundary. Certain models of quantum gravity show that a theory containing gravity in a volume can be equivalent to a different theory without gravity defined on that volume's boundary. These examples give precise meaning to the holographic idea in particular mathematical settings, but whether the same framework directly describes the black holes in our universe remains uncertain. Still, it has changed the way many physicists think. The inside and outside of a black hole may not be independent regions separated in the simple way classical geometry suggests. Information that appears trapped in the interior might be encoded non-locally in degrees of freedom associated with the horizon or the surrounding quantum state. The information problem may therefore be less about a substance escaping from a prison and more about discovering that the prison and the outside world were never separate systems at the deepest level. Observations will increasingly shape these debates. Future gravitational wave detectors on Earth should hear mergers at far greater distances and with much higher precision. Space-based instruments are expected to detect lower frequency waves from massive black holes orbiting one another for months or years before collision, allowing astronomers to follow their approach rather than catching only the final instant. Such signals could reveal how galaxies merge, how central black holes form pairs, and whether some binaries stall before reaching the point of collision. A network of more sensitive detectors may identify thousands of black holes that emit no light, building a census based on gravity alone. At the same time, expanded horizon-scale telescope arrays may produce sharper images and eventually moving sequences of material circling near black holes. Instead of a blurred ring reconstructed over several nights, astronomers may watch bright structures evolve, trace magnetic fields, and connect activity near the horizon with jets extending far beyond the host galaxy. These observations could measure spin more accurately and test whether the dark silhouette remains consistent across different black holes. X-ray missions will continue examining the innermost regions of accretion disks, while infrared telescopes will search for the faint galaxies hosting the earliest growing black holes. No single instrument will solve the mystery, The next advance will likely come from combining light, gravitational waves, particle physics, and precise simulations into one account of the same event. The deeper significance of this work is easy to miss because black holes are often presented as exotic objects located safely far away. In reality, they have become meeting points for nearly every major question in fundamental physics. They connect stellar evolution with galactic history, gravity with thermodynamics, information with geometry, and the early universe with observatories operating today. They force science to confront a rare situation in which the best theories available are each successful on their own, but incomplete together. The future may reveal that black holes are exactly the objects predicted by general relativity, all the way down to scales we can never directly reach. It may reveal small deviations that point toward quantum gravity. It may show that primordial black holes exist, that intermediate mass objects form the missing links in galactic growth, or that the earliest supermassive black holes followed several different paths. Some questions may remain inaccessible because no signal can return from beyond the horizon. But history has repeatedly shown that direct access is not the only path to knowledge. Gravity moves stars. Radiation records the motion of gas. Space-time carries the memory of collisions. And quantum theory leaves constraints even where observation seems impossible. Black holes began as objects defined by what could never be seen. They have become some of the most information-rich laboratories in the universe. Their story is unfinished because every new way of observing them reveals another boundary behind the one just crossed. And somewhere within that continuing pursuit may be an answer larger than the history of black holes themselves. Whether space and time are the foundation of reality, or only the visible surface of something deeper still. Black holes began as a daring idea and became one of the greatest discoveries in modern science. If you enjoyed this journey, please like the video, subscribe to the channel, and thank you for watching.